so I'm going to repeat everything. Thank you for the invitation to present some of the work I've been doing with Mike Sen, also at CCPR. As I said in the quick introduction, this is very early work, but it's also very basic in the sense that I will be most likely preaching to the cohort today. This is mostly intended for non-demographers. So I don't think there's anything in what I'm going to say that any student with a semester works of demographic methods couldn't figure out. So this said, I need to also get sharing screen. So I think I've been disabled while I rebooted. So I would like to do that. Okay.
All right, I did share it.
All right. Yep. Thank you. So let's see. We're okay. I'm going to share my brother, which is now on the wrong page, but okay. So there's a number of trackers that probably anyone who's paid attention to COVID pandemic knows about, both for estimates and projection. This is probably one of the most recent, most used tracker for numbers of cases and deaths. This is from the Johns Hopkins. And recently it started to provide something called to compare mortality across countries. And in this type of table, you have number of cases, number of deaths, and particularly deaths divided by population. And this is what has kind of started me on this track of trying to provide a better metric than deaths per 100,000 population. And on the projection side, there's also a number of sites. This is, again, one of the most commonly used for projection from IHME with, current deaths, projected number of deaths, and so on. So there's a number of alternative sources on our CCPR site. If you're interested in looking at some of them, we have a page under services here that has a number of those links. And today, I'm not going to try to adjudicate between any of those. I'm just going to use. And can you hear me again? I'm having problems.
We lost you for a second, but you're back.
Okay, I think it's when I try to share for some reason. Well, again, wave at me if you lose me. So yeah, today I'm not going to try to say anything about the projection. Our point is that the situation is still changing very quickly, and there's not really a point to try to adjudicate between those estimates and projections yet. But in the meantime, we'll try to provide to non-demographers some metric and suggestion. But our take is still that, as was the case with the HIV/AIDS pandemic, deaths are a better basis for tracking the pandemic than cases. We know even, deaths are underreported. I mean, we suspect they are, but relative undercount is still of a different magnitude. So they might be undercounted by maybe 20, 30, 40%, but not by a factor of 10 or 20. So this death per population is, of course, a good start. We want to compare number of cases or number of deaths in countries of relatively similar size. But this still misses a number of important properties that demographers care about. And the first thing, again, is the first thing, I guess, for all demographers is to make this difference between a ratio and a rate. So if you look at the US ratio from the table I've just shown you from Johns Hopkins, it's now 24.3 deaths per 100,000, which is very small if you compare to the CDR in the crude death rate in the US, which would be in the same metric, 884. But of course, they don't occur in the same amount of time. So the part that is often missed in the crude death rate is the time dimension here, because often we talk about 1 year and we measure time in 1 year units, so it's not there. So the first thing we do is to add the time dimension here by looking at the time that going through WHO reports, when was the first death reported in a particular area, and only count the calculate the crude death rate from COVID mortality only from that point up to the present or up to the date of the projections. The second thing that is obvious to any demographer is that we need to standardize this measure. We know there's a strong age pattern of COVID-19 mortality, so that we need to adjust for this. Unfortunately, direct age standardization. Do you still have issue with my? Okay. All right. Am I back?
You're back.
Okay, yeah, I keep getting messages about problem with my audio and I have to click cancel to get back, but sorry about this. The thing we cannot always do is to directly age standardize because a number of countries don't give a lot of detail. Sometimes they do, but only up to like deaths under 60, 60 to 80, 80 plus. And so now that the CDC has given us a pretty detailed age breakdown by 10-year age group, we can do an indirect standardization, something like the comparative mortality ratio, where we compare actual deaths to the deaths we would have with the CDC age pattern and the actual age distribution in a particular area.
And Patrick, can you tell us what the abbreviations are, ED, FD?
Oh yes, sorry, this is a comparative COVID mortality ratio, so similar. And this is from the first death to the estimate of the current count of deaths or the projected number of deaths. For HME, it's August 4th, I think it is.
Are these intended to account for the time period?
Yes, exactly. So this is to measure the length of time. Actually, it's a population multiplied by this T length of time, and that's the adjustment. And the third one is to, so the comparative mortality ratio are much better because it's age standardized. It's still not a metric that is very intuitive. So the last thing we do is we try to convert those in decline in life expectancy at birth. We can only do that at the level of the country because that's where we have life table. And the process is similar to this is the reverse of the process of deleting a cause from a multiple decrement life table to an associated single decrement life table. So we calculate Chiang's ratio and we adjust probably by these ratios. Now the ratio are bigger than 1, so we compare the new number of deaths we project compared to the counterfactual that would have been projected without COVID-19. So that's a ratio that is bigger than 1. And since the probability of survival is less than 1, when we raise this, of course, the probability of survival declines. So from this, we can complete the life table. So I'm going to try to go fast and catch up a little bit of time. I'm not going to go through all the data we use. So we use WHO to get the first report, a weekly report, actually daily report to. Sorry.
Lost you again for a second.
Yeah, so okay, here, I have to cancel and switch screen. Okay, and so this is what we use for the estimated of first deaths in the country. We use the UN for meat population. We use the Census Bureau for the states, and we use the UN again for life table. So very quickly, some of the results. So you see that when we adjust for the period, for example, in high mortality, COVID mortality places, we get a number for like the state of New York of 879 per 100,000, which is actually higher than the crude death rate, suggesting more than a doubling of the number of deaths in the state. We also get number for the province of China, Hubei in China, which is about 60 million, a number that is more comparable to other countries because now we've adjusted instead of divided by a huge denominator of 1.4 billion. So this is, we look at, I didn't say, right now, I mean, we're setting this up in R so we can actually have all the countries and all the states we want. We started with only a selected number, 15 countries and 9 states, which were when we started mid-April, the areas that had at least 1,000 deaths at the time. But the number, of course, is much larger now. And when we do the comparative mortality ratio, when we standardize for age, what is not surprising is that the ratio tend to go down in the European country that have older population relative to the US, and the ratio goes up in developing countries like Brazil, Turkey, Iran, that have higher, younger age structure than the US. But we believe this gives us a better basis for making this comparison. And then last, in terms of life expectancy at birth, this is the result we get now. In the projection, again, shouldn't make too much of it. The number are projected to increase in Sweden because IAHME incorporates the fairly lax social distancing rule. But we get for a number of countries estimates of 1/2 of a year in life expectancy, which doesn't seem to be maybe a whole lot. But if you look at decline in life expectancy due to the last two public health crises in the US, HIV/AIDS, for example, the largest one-year drop was 0.3 of a year between 92 and 93. And for the opioid epidemic, it was 0.3 as well, but over a couple of years. So these are actually pretty substantial decline. But again, I don't want to make too much about the actual numbers because they're changing and we're learning every new things every day. I think some of the direction we're working at is to include more countries and states. The question is, what is the right level to make this comparison? The US states might actually be a little bit too much still. But the county might be too small to extend in large metropolitan area. There's no reason for us in LA, for example, to separate LA County from Riverside, Orange County, and so on. So we'll be working on this. The second thing is now we started to standardize just on age, but now we can do both age and sex because the CDC has provided us the breakdown. And the third question is, what is the relationship between COVID-19 estimates of deaths and excess deaths? The adjustment we did is kind of standard life table assumption of independence. So assuming this is no effect on other causes of death, but there's evidence so far from CDC seems to suggest that the number of excess deaths is actually higher than the number of COVID deaths. So this is the third things that we're going to be looking at. Sorry for going long and sorry for the interruptions in my audio.
Thank you. Great job, Patrick. We apologize for the technical problems. We're getting some questions from me, but we're not getting a lot of questions from the audience. So let me just start with the big thing I was chatting about, which is thinking about the time element here. It's not clear to me why I have this intuition, but it just seems to me this isn't like a regular cause of death in terms of risk of exposure. I don't know why we should divide the number of deaths by the 1 month since the epidemic's been in place, or essentially, or why we should consider any fixed time period as the person years of exposure. So that's kind of a philosophical question. Second question, does it make any difference for our calculation of life expectancy?
So second is easier to understand, to respond. Right now it doesn't. So because we are only looking at life expectancy for a calendar year for 2020. So it doesn't matter as long as we don't have deaths. We don't include deaths that start that are outside of that window. So we are not adjusting for the length of time. The adjustment for length of time. I think well, the first reason is to give a metric that is closer to what accrued death rate.
We lost you again.
Yes. Okay.
Okay.
I should be back. So yeah, it's to give something that is comparable to the accrued death rate. So that we can compare total deaths and deaths from COVID across areas. I don't know if that's what you're getting at, but you're probably getting a lower rate in the first months after the first death that you might be getting in the second, and then the longer the period gets, maybe this is declining. And this is something actually that is potentially interesting to show you where the intensity of the epidemic. So, for example, if you just dividing deaths by
let me just interrupt a little bit.
Yep.
This seems, is this a desirable property for a measure of mortality, that it changes depending on when we decided the epidemic started or not? I mean, we're thinking about the lethality of the disease and the total impact of death. It seems to me that maybe we're trying to shoehorn this into our traditional demographic way of thinking, and it might not be applicable now. I'm asking you this as someone who's using these myself, so I'm trying to kind of push back against some of the things I myself am doing and get another opinion.
Yeah, I see what you mean. I mean, the one possibility is to do instead, and that's, I think that was in the first draft, instead of starting the clock at the first deaths in the country, we started the clock at pretty much, the first deaths in the world in China, which was pretty much the same as starting on January 1st. So that's another option, which you may think is more acceptable. I think that the reason, what is, I think the property that is somewhat desirable is that this crude death rate would change over time and possibly go down over time. If you just divide by population, the cumulative count of deaths, it just keeps going up. But if you standardize by time, it goes up and then it goes down. And I think that's a desirable property for that measure.
Great, thank you. So we have a question from Claude Fisher. For the non-demographer population, is the takeaway that COVID-19 will cost about a half a year in life expectancy? Is that kind of what you're thinking as a good summary outcome?
Well, no, not really. Well, I was trying to really illustrate the properties and the measure. The data, I think it's really too early to draw any conclusion from the data. We don't know if what is the percent undercount on the current death estimates. We don't know how good the projections are. I think we're getting a sense that things are converging a little bit. Sorry, we're starting to get a decent picture, I think, for probably the first 6 months of 2020. We have no idea if there's what would be the second half of the year. I think it's safe to say that it's probably an underestimate. I mean, it's way more likely to go up than to go down. So the number that we have with this half a year for the US is based on 130,000 deaths in the country by August 8th. The number, actually, when I was showing you sharing the sites, I see the number have already gone up by 10%. I don't think they can go down. I can only think of reason why they would go up. We could, find out that there's a lot more COVID deaths that were not reported. We can find out that there's a second wave. We can find out a number, So I think when we did the first time we did this, we did a projection with the projection were at 60,000, and with 60,000 we were getting 0.3, I think, of a year down, and we've already exceeded that number. So it's almost certainly more than that, and I think it's very likely to be even more than half a year. But so I would say just take away, because I don't think there's any number that you can, or projection that you can really take to the bank at this point.
Great. Okay, let's pause there. We'll come back, I think, at the end of the session to discuss some of these more philosophical questions. I think they're hard questions. Anybody who has answers to them, please chime into chat and we can get Patrick to answer, to respond to your potential answers. I guess a question I have is just, is this unprecedented for demographic thinking, that we have something that doesn't seem to fit into our regular way of measuring things? Is this unprecedented for epidemiological thinking? I would be surprised if the answer to either of those is that this is unprecedented, but maybe it is. It requires completely new ways of thinking. Okay, so thank you for the talk, Patrick, and now we're going to switch over to Miguel. Miguel, I think, is in a little bit of a reverse situation. He's not at the beginning of his work. They actually have a fully formed paper with lots of supplementary materials that is available. Maybe if Alexia could type in the link to that paper in the chat room, that would be great. So Miguel's task is to reduce this great amount of work that they've already done to only 10 minutes. So good. Thanks for joining us, and we look forward to the talk, Miguel.
Thank you, everyone. Thank you, Josh, for inviting me, and thank you, everyone, for attending to this talk. So I will try to share first the screen. Let's see. Okay. So everyone sees the screen already? Can you hear me?
We saw it before you went to full screen, and then it just went
Oh.
black.
Okay, so everyone can hear me, I guess? Okay, no, it's better.
We can hear you perfectly, but we can only see the title bar of your slides.
Yeah, maybe try leaving the full screen thing.
Okay.
There we go.
Okay, so we can see this if you don't go full screen, and the
Okay.
font is big enough for us to see, so you can just leave it like this.
Okay. Maybe it's better to do it on this way. So as Josh was introducing before, this is a joint work with Vanessa Di Lego, Alexia Preskovich, and Bernardo, that they are all present in this meeting. Now, what is the main motivation for this paper? And before explaining or giving you like the typical motivation, I think that is better to tell you why we started doing this kind of project. And in principle is because before we started to being in lockdown, we were already worried that most of the countries, at least in Western European countries, they were not doing anything to stop the propagation of the COVID-19. So the first idea that we were having, and when we were running the first models by mid-March, was to give a public awareness of the consequences of the COVID-19 pandemic. So one of the things that we were trying first is to estimate what will be the total number of deaths in the case that countries will not intervene. Once that we will have these estimates telling what will be the consequences of introducing the typical measures that were introduced already in Asian countries, that are the non-pharmaceutical interventions, like massive testing and isolating people and social distancing. Here, what we were doing was testing and isolation. Now, this is already in the paper, so this is one part of the paper, but what I will focus today is in what I think that is the most important contribution of the paper, that is the part that can help to monitor the evolution of the pandemic. So what we are doing is the typical H-structure epidemiological model. And one of the things that we have to deal with is that there are two important technical issues when we are trying to replicate the evolution of the pandemic. The first thing is, as Patrick was mentioning, is that the number of cases, so the infected people, is highly underreported, and this is caused by the fact that there are many asymptomatic individuals. This was already shown by many reports by the Imperial College. Now, what we are going to do here, or what we have done, is to try to replicate the evolution of the total number of deaths. And what we have to face here is that there is also a huge uncertainty in the mortality data. So we know that there is huge underreporting, but there is probably also reporting cases like those reported in the country of Belgium. So what we have done in this work is we have constructed an H-structure shade model, and we are trying to replicate the mortality, the total number of deaths. In order to do that, we have plugged in the case fatality rate but we are taking into account the probable number of asymptomatic individuals. So we are calculating what is the probability of having asymptomatic individuals in the model, and we obtain similar results as those of the Imperial College. And in order to avoid the over-reporting, we are also introducing the non-COVID mortality, so the observed mortality before the COVID. And one of the main contributions of this paper, there are two main, but one of the main contributions is that we are not doing the standard Bayesian approach. So we are not using the standard Bayesian approach, we are using the Bayesian melding. And why are we doing this? What we saw is that the data is extremely bad. So we cannot replicate a model just based purely on the data that we have. So there is a huge uncertainty in the data. And what the Bayesian melding is allowing us is to take into account simultaneously the information that the model is reporting and also what the data is telling us. So the Bayesian melding in this particular case will help us to say, okay, given that the existing safe models, we know that they are capable since decades to replicate very well the evolution of epidemics, we are going to rely on the information that these models are giving us. So we are giving exactly the same weight of the information reported by the model to the weight reported by the data. We have calibrated the model, so the total number of deaths for the case of Heuveline in China, for the very first 80 days, we have run the Bayesian melding, and we have obtained 500 different models that they are capable of replicating well the evolution of the pandemic in China. So we will have 500 different set of parameters, and we have used these 500 different models in 200 countries. We have calculated the total number of deaths, and afterwards we have implemented the non-pharmaceutical interventions. So we are checking what will be the impact in these 200 countries, depending on the level of testing that a country is performing, coupled with isolation, what will be the effect of herd immunity, and also what will be the effect of the day of intervention. Now, the first part of the paper is about what is the role of the demographic factors on the global fatality rates that we are observing. And what we have detected is that there are two major, there are many more, but the ones that we have focused here is that there are two major demographic factors. One is the population size, and the other one is the age distribution of the population. In terms of the population size, what we are seeing in this figure is what is the probability of getting infected depending on the size of the population. So we are contrasting here the case of Iceland, that is a country with a very small population that is around 350,000 individuals. It's slightly less than that, according to the United Nations, compared to Brazil and China. And what we can see is that in a small population, the probability of getting infected early on is much higher than in a larger population. So the population size is affecting mainly on the propagation speed.
Miguel, can you use your mouse just to show us what you're saying? How something happens earlier or later?
Now, what we have here are different lines. Each one of the lines correspond to the different models based on the different parametric estimates from the Bayesian melding approach. And the thick line that we are seeing here is the average across all the simulations for each one of the countries. So here is the case of Iceland, and this other one is for Brazil, and the green lines correspond to the case of China. Now, with respect to the age distribution of the population, this is already quite clear. It wasn't so evident 2 months ago, but what we know is that the fatality rate, the infection, so the case fatality rate is highly dependent on age. So as individual age has a higher probability of dying once that the individual is infected. So in principle, those countries that they have more age populations, they will have, so that is represented by the mean age of the population. So those who have a mean age of the population that is high, they will face, in principle, much higher infection fatality rates. So here, what I'm presenting is our estimates of the infection fatality rate. So it's not case fatality rate, so it's infection fatality rate. So we have here in these dots, that are the blue dots, European countries that they are usually more AIDS. This dot here correspond to Japan, and the second one is Italy. And on the other side, we have those countries with, who have low mean age of the population that are represented mainly by African countries. Now, the gray dots here correspond to the non-COVID death rates. So as Patrick was pointing out before, in many countries, like in the US, what we will see is that if there is no intervention, we can observe almost a doubling in the number of deaths relative to the observed number of deaths from previous years. Whereas the number of deaths that we are expecting in African countries, given that they have a much younger population, the deaths from COVID, they will be much lower relative to the deaths from other causes. Now, we have the first part, that is what will happen in the case of not intervening. And now what we are focusing here is what will be the impact of the non-pharmaceutical intervention. So what we have modeled in this work is what will happen if we have different levels of testing, and once that the individual is positively tested, will be isolated. What happens if we start intervening and testing and isolating people at different weeks? And also what will be the effect of herd immunity. And the herd immunity in this case is calculated assuming what is the proportion of people that they are susceptible to getting infected. So what we are seeing in this figure is exactly the same figure as before, but now for columns represent the different levels of testing. So 9% will correspond to only testing critical and severe individuals with critical and severe symptoms. This other one is only half individuals that they are presenting, that they are symptomatic. So half of the symptomatic individuals, and so on and so forth, as you can read here. So the columns correspond to the levels of testing, and the rows correspond to the different degrees of herd immunity. So the herd immunity of 25%, so it means that only 75% of the population, of the initial population, can get infected, or 50%, which is this middle row, or that 75% they have already herd immunity. And this, what we are calculating here, is the infection fatality rate. So the take-home message, but in principle is clear, that non-fatality rates, non-pharmaceutical interventions, what is affecting is on the probability of getting infected. But the infection fatality rate is the probability of dying conditional on being infected. So what we are seeing is that the infection fatality rate in principle shouldn't be affected by the non-pharmaceutical interventions. And this is a property that we are going to use later on for calculating, which what we think is the other novelty of the paper, that is for being able to estimate what are the probable number of infected individuals. So we are going to use this estimated infection fatality rate. And as we all know, the infection fatality rate are the deaths, in this case from COVID, divided by the total number of infected people from COVID. And we can split it into two ratios. One is this fraction of infected and detected individuals among the total infected. And this is calculated depending on the level of testing that a government is performing. And this is the case fatality rate. Now, the point is that the case fatality rate, as we have estimated, can be calculated based on the different levels of testings. So once that we have estimated the infection fatality rate, we have played around with the model for different levels of testing and calculate what is the case fatality rate. Now, one of the important properties in this case is as we have shown, is that the infection fatality rate is in principle unique for each one of the countries, given the demographic characteristics. So this is a very important property because it doesn't depend on the non-pharmaceutical interventions. And the other property is that just depends on the demographic characteristics. So this raises the convenience that as demographers, we can provide a lot of help to epidemiologists. So the way that we are going to indirectly estimate the number of infected individuals in principle is given the infection fatality rate from a country and the case fatality rate reported by the government, so of each country, we can indirectly infer the total number of infected individuals by calculating what is this level of testing. So it will be the level of testing such that it coincides with the case fatality rate. So what we are plotting actually are like ISO infection fatality curves for each one of the countries depending on the demographics. So here, this is the plot that we have in the paper. So this is a very important plot. So we have this, what I'm calling the ISO infection curves, is unique for each one of the countries given the demographics. And we are reporting here the ISO infection curves for Italy, Spain, Austria, United States, China, Brazil, India, and Niger. Now, in order to properly read this, so on the vertical axis, we have the case fatality rate, and the horizontal axis, we have the level of testing. But the level of testing in this particular case depends on whether you are testing symptomatic or asymptomatic. So if I explain a little bit more, is this gray shaded area, what represents is the level of testing for symptomatic individuals. So if we are on the left-hand side of the gray shaded area, it means, so in this area, it means that we are only testing symptomatic individuals, that they are critical or severe. If we are on the right-hand side of this shaded area, so if the level of testing is here at this frontier, what it means is that we are testing all symptomatic individuals. And whenever that we start having values here, it will imply that we are testing already 100% of the symptomatic individuals plus asymptomatic individuals. And based on the reports from April 21st, here for each one of the countries, we are computing what is in these circles, so cross circles, what will be exactly the case fatality rate that will correspond to each one of the specific countries. So what we are seeing is that actually based on the model, what we are obtaining is that most of the countries, they are just testing those who are critical or severe. So mainly those who are at hospitals. Only 2 countries here, they are not doing that, is United States and Austria. Austria is one of the leading countries in terms of tests per capita. So I will move to the next slide. So yesterday I was collecting new data from the ECDC, so it's the European CDC, and I was collecting data on the infected number of detected cases and the case fatality rate. And then I was estimating based on these ISO curves, the testing level that will correspond to the case fatality rate reported. So we were obtaining that the testing level is around 23% for the case of Austria, which means that this is around half of the people who are symptomatic. If we move to the US, it's around 12%, which is above the values for the critical and severe, but is not reaching the level of testing of Austria. Now, from the level of testing and based on the infection fatality rate, better said, based on the testing level and taking the infection fatality rate, we can divide this value by this one, that is in percent, and we can obtain the total infected individuals. So the infected individuals is, in the US, we are estimating there is right now around 11 million people. And this will give a herd immunity above 3%. This is close to the report, I mean, the serological test done for, I think that for Santa Barbara. This afternoon exactly was reported the seropositive test in Spain before the presentation, and it was done 2 weeks ago, and they were reporting that it was around 5%. So 6% is quite possible. And I was adding France and United Kingdom because I was puzzled to see case fatality rates that they were so high. And actually it means that for this case fatality rate, they are testing much less than those who are critical and severe.
Miguel, just in the interest of discussion, I think you have one more slide. So,
yeah. Okay. So this is pretty much, I think that everyone will understand the point. Afterwards, they can check. But so we have 2 contributions as far as we know, is using the Bayesian melding in this particular case, although Raftery probably has already presented their own estimates a few weeks ago. But also the indirect estimation method that I have presented. And we have a few caveats to report that we are not taking into account in our simulations, the underlying health conditions, country-specific healthcare system capacity, gender differences, and social distances and living arrangements. Although for the many of these caveats will not apply whenever that they are non-pharmaceutical intervention. So whenever that these caveats are not non-pharmaceutical interventions, in principle, this won't affect on the on our indirect method. So thank you for your attention.
Super, thank you so much, Miguel. I'm seeing applause. Here we have lots of questions in the chat room. I'm going to go in reverse order. Tim Miller is saying, how about running this on New York City? Could you compare to some of the antibody prevalence and the serotests? Or I guess the general question. Have you thought about comparing this to the serotests?
So we haven't done it yet. Yeah, I mean, we will be super happy. We have to find what is the population distribution and the age-specific death rates for New York. So Tim, if you have it and you pass it to us, it will take just an hour to do all the estimations for New York City. So, or if you tell us where to find the data, we will be super happy.
Awesome,
okay.
I'll pass it along.
Okay.
Leora is asking about the interaction between age structure and development and the progress of the spread of the infection. In other words, so right now you're kind of treating every country equally in some sense, but is there going to be some kind of higher level at which age structure is going to interact with the spread of the disease because the countries with younger age structures are less developed?
So we have the age, but we have the underlying assumption that everyone has exactly the same probability of getting infected regardless of the age. But I think that most of the reports are showing that no matter what is the age and no matter what is the gender, the probability of getting infected is exactly the same. Another issue is it will depend, I guess, but this is better suited with agent-based models, whether there are different social behaviors. And this is something that we are not taking into account in reality in the model. So it would be a completely different model.
Okay, I think that's probably what Leora was asking. Is there another kind of story here about what we should expect in the long term, where the older, more developed countries can actually control the epidemic more, but I'll leave it as a rhetorical question. And I think your answer, it would require a different model, is probably useful. Let's see. Household age composition. Should we think about this in terms of what happens and how the disease progresses?
So if we want to monitor at each point in time the evolution of COVID, for sure. For the indirect estimation method, given that this, what we are reporting here is a back of the envelope calculation, no. Because what we are already calculating is conditional, I think that is, conditional on being infected. Then we are calculating what is the level of testing, and then we are backing up the total infected individuals. So the only measure that we need to have for this indirect estimation method is just the case fatality rate, which does not depend on the living arrangement.
Okay, so great controversy over your first figure where you showed Iceland and Brazil all in the same figure, and they all looked like they had exactly the same thing happen, but at different timing. Everybody's saying, wait a second, population size shouldn't matter, it should only be density. Let me read the two comments. John Wilmoth, I do not understand the claim about population size affecting the timing of the epidemic. If the level of the infection is the same, why would population size matter? And then we have Robert and Magali, one of the two. Isn't population density a stronger driver of the epidemic than population size? Self-identified as Magali. Thank you.
Completely right, but this is something that we are not, we don't have in the model. So that's why, rather than focusing on population density, we are just taking, we are analyzing the population size. But it's true. In principle, the density will be much more important than the population size itself. Now, again, for the indirect estimation method, it doesn't matter.
Okay. I have a question about the isoquants, which I thought was very clever, trying to kind of work backwards. Why don't we see a kink where you change regimes? Why is it just a smooth curve where you go from testing 100%, 100% of the tests are symptomatic individuals to a mix of symptomatic and asymptomatic? Shouldn't that kink the curve? Shouldn't there be a different relationship if we're only testing symptomatic people than if we're doing a mix?
Because once that, so I probably explained myself not very well. So the level of testing in this case is like a continuum. Here is the threshold that we have tested all the symptomatic individuals, but none of the asymptomatic individuals. Once that we start moving to this other side, we have already tested all the symptomatic individuals, and on top of that, we start testing the asymptomatic individuals. And that's the reason why you don't have any kink. And it's a super important
why would the relationship between testing and case fatality not change depending on whether we're testing people who were symptomatic and asymptomatic?
Can you repeat?
Okay, maybe this is too technical a question. We're kind of running out of time. Let's see. I think we're getting, I think I've asked, can anybody turn off their mic if I haven't asked their question and go ahead and ask their question?
Yeah, I had a question. This is Patrick. So I think the assumption, if I understood correctly, is working back, assuming a constant rate of fatality, at least in a country given a given age structure. But I think there's over time there seems to be a nonlinear relationship between the two, number of cases and number of deaths. There seems to be tipping points. For example, we saw in New York with the hospital capacity to handle intensive care units, for example. I think it was the same. If you look regionally in France or in Italy, there seems to be region where, so-called hotspot, where hospitals at some point couldn't deal with the influx of patients, and then the case fatality rate shoot up at that point.
Yeah, in principle, that will be an issue. So if this doesn't happen regularly in the countries that we are analyzing, then we don't have any problem. This is the problem that we are contemplating for many of the non-developing countries. That this might happen, and then we will have much higher death, infection fatality rates than the ones that we are reporting. So in the discussion, we are already saying something about that. And I don't know whether, but well, in principle, yes, Patrick, you're right. But this is one of the caveats that we cannot control for at the moment.
Excellent. Okay, so on that note, let us end our official session and thank both our speakers. Bravo. Wonderful talks, great discussion. I thank the audience for all their questions. I'm going to keep everything open so we can continue to ask questions, but thank you so much for joining us. You're both, we should add you to, if you want to be added to our announcement list, we'd love to have you join in the audience in future sessions.